recording right now. Okay. So the first thing we wanted to discuss today was the solution to your homework number 1. And I guess all of you have submitted homework number 1 already. And we're going to start the grading pretty soon, as soon as the APIs are available. Now, what I'm going to do today very quickly in the beginning is that I'll go through the solution of homework number 1. And as you will see that some of these solutions are pretty much intuitive. So you don't even need to do a lot of calculations to come up with the solutions. So for example, if you just look into your problem number 1, which was again a voltage division problem, you were asked to find out what is the V0 over Vs. So you wanted to find out what is the ratio of this voltage to the input voltage. And as we have solved the problem in the class, the way you approach these kind of problems is that you start from the output side and you start to simplify the resistances or any other components that's there in the circuit. So you start from the right hand side, which is V0, and you traverse towards left, toward your input. So you start from your output, you traverse toward your input. So what you see first, you have this 30 kilo ohm and the 10 kilo ohm resistance in series. So these two resistances are in series. So overall, you'll see a 40 kilo ohm when you see those two resistances which are in series. 30 plus 10, that will give you 40. Now that 40 kilo ohm will be in parallel with this 40 kilo ohm, which is R2. So you have two resistances which are in parallel and both of them are 40 kilo ohms. So what is the effective resistance? It's half of those two. Because you know that the formula for parallel resistances Rx and Ry would be Rx times Ry divided by Rx plus Ry. That's the formula for two parallel resistances, which are Rx and Ry. Now, if you put the values and if you consider that Rx and Ry are equal, then on the numerator you have Rx squared, and in the denominator you have 2 times Rx, just assuming that they are equal. So which means that one of the Rx's will get cancelled from numerator and denominator, and you will be left with Rx over 2. So when you have two resistances which are equal and are in parallel, the effective resistance will be half of any of those. If you have 3 resistances which are equal and in parallel, the effective resistance will be any of those resistances divided by 3. So what I'm saying is that you don't even need to calculate some of these scenarios. Let's say you have 3 resistances and they are in parallel. And let's assume each one of them is 30 kilo. So 30, 30, and 30 kilo. So the effective resistance that you will see, looking from either side, because this is the network which is reciprocal. So looking at any of these sides, your overall resistance will be 30 kilo divided by 3, which is 10 kilo. If you have 4 of them in parallel, it will be divided by 4, given that all of them are equal. So these are certain scenarios, special scenarios, where you don't even need to calculate things. You can just remember that, okay, if they are equal, the effective value will just be divided by 2. That's what is happening here. So you have a 40 kilo ohm as R2, and you have another 40 kilo ohm, which is the series combination of R3 and R4. So effectively, you'll see a 20 kilo ohm looking here. So Rx will be 40 in parallel with 40, that is 20 kilo ohms. Now you are at this point where you have a series resistance R1 and then an effective resistance looking into right hand side, which is again 20 kilo ohms. So you will have a voltage division between this R1 20 kilo ohms and this Rx, which is the effective resistance looking into the right hand side at the right hand terminal of this node R1 or resistance R1. So you know what that voltage division will be. That will be 20 divided by 20 plus 20. That gives you half directly. So that's the voltage division happening between R1 and whatever is available on the right hand side of R1. Okay. So you know what would be the voltage at this right hand side of the R1 resistance, which is also the left hand side of this R3 resistance. So you know the voltage at this point. What would be the voltage here? That would be a voltage division between R3 and R4. So the second term is a voltage division between R3 and R4. And because we are taking the output across R4, it will be R4 divided by R4 plus R3. Remember that voltage divisions are proportional to the resistance across which you are taking the voltage. current division are inversely proportional to the resistance across which you're taking the current. Go back to the first lecture and remember that if you just want to refresh your memory. So we are taking the voltage across the R4 resistance. So it will be, the voltage division will be proportional to R4. So you have the two voltage divisions, and the multiplication of those two factors will give you the final output. And again, it's less than 1, it's 1/8. Because this is a passive network, passive networks cannot give you any kind of voltage gain. You will only have some kind of attenuation, which is another way of saying that you have loss or your gain is less than 1. If you represent that in dB, it will be less than 0 dB. So it will be minus something, negative something dB. Okay. Problem number 2 was very similar. You had a 200 kilo ohm, 200 kilo ohm. These are the two resistances on the right-hand side, R3 and R4. Now, interestingly, R3 and R4, they are, as you solve this problem similar to the previous problem, you'll see that R3 and R4 are in series, right? If you're looking from the left-hand side. So we'll use the same approach as we did in the previous problem. We'll try to find out what's the effective resistance looking from the left-hand side at this point, and that would be 400 kilo ohms. Now notice that this 400 kilo ohm is much larger than R2. R2 was 1 kilo ohm. So if you want, you can calculate what is 1 kilo ohm in parallel with 400 kilo ohm, but that is kind of superfluous. You don't need to do that, because if one resistance is very small, when you have, let's say one of them is 30 ohms and the rest of them are 30 kilo ohms in this parallel network, what would be the effective resistance? It will be almost equal to the smallest resistance, because this resistance is very small as compared to the other two. Okay? So same thing is happening here, that you have one resistance which is 1 kilo ohm, the other resistance is 400 kilo. So this is 400 times larger than the other one. If you want to do an exact calculation, it would be 1 multiplied by 400 divided by 1 plus 400. So that is 400 divided by 401, which is almost equal to 1. So in cases like this, you don't even need to calculate that 0.99 something, that exact value, because for all practical purposes, this is equal to 1. So you can estimate, you can approximate this resistance to be 1K. And that is something of a valid assumption, because again, as I talked in the class earlier, all electronic components have some kind of a tolerance. So if you have a 1K resistance, it can never be exactly 1K. It could be 1.01K, it could be 0.99K, it could even be 0.97K. You do not know the value exactly, and you cannot control that value to that much accuracy. So what's the point of doing that exact calculation? It's much better if you can do a faster calculation and come up with an answer which will have maybe 1% error, but that's okay. That's how we design circuits. You don't really go for that 5-digit accuracy when you are designing circuits. Yeah. Because there's always variations, there are always change, there is always some factors which you cannot control. So doing an exact accurate calculation does not matter in circuit design. So effectively what you will have here is this 1 kilo ohm, and looking at the right hand side, you have a 400 kilo ohms. So the effective parallel resistance of 1 kilo ohm and 400 kilo ohms will be equal to 1 kilo ohm. So now you have this very simple network that you have your voltage source, you have a 1 kilo ohm resistance here and a 1 kilo ohm resistance here. So the first voltage division you'll have between these two 1 kilo ohm resistances, that's this term. The second term is again a voltage, because you want to find out this voltage and not this point's voltage. What you did here with this voltage division is that you found out this point's voltage, and that is the ratio of this point to the input is 1K divided by 1K plus 1K. But eventually you want to find out the voltage ratio at this point. So for that, you have to take care of the second voltage division, and the overall voltage division factor will be 1/4 if you just do the calculations. Third one, it's a little bit different, but again, the same formulas and same theories apply. It's a current division instead of a voltage division. So just apply your current division formulas, which are a dual of your voltage divisions. Okay, and the approach will still be similar. You start at the output side and you traverse back towards the input. What is the first thing you see? You see a parallel combination of these two resistances, which are 10 ohms and 20 ohms. And the parallel combination of 10 ohms and 20 ohms will be 200 divided by 30, so around 6.67 ohms. But the important thing is that 6.67 ohms, which is the parallel combination of these two, that is much smaller than this resistance R2. So if you have a large resistance in series with a very small resistance, so you have a large resistance first and then a very small resistance here. What would be the effective series resistance of these two combinations or these two resistances? It will be almost equal to the larger resistance, because 100 kilo ohm plus 6 ohms is almost equal to 100 kilo ohms. It does not matter. It does not add any value to do that exact calculation at this point. So you can just assume that the overall resistance is 100 kilo ohm looking at this point. And then you can do this small calculation that if you have a 300 kilo ohm as R1 and you have this 100 kilo ohm in series with 10 ohms and 20 ohms, so you have this overall effective network, but then again, this resistance, the overall resistance is still 100 kilo ohm. So you can just do a current division of that. You can find out that 1/4 of the original current was going through this branch. And then you'll do the second current division, because right now you just did the current division at this point. What is the current being divided into this branch and that branch? Eventually, you need to find out what is the current going through this branch. So that's why you need to do a second current division. And that second current division is something that you can just do and find out what is the overall gain. All right, so this is the first current division and this is the second current division, giving you the overall gain of 1/4. Fourth problem, it's an amplifier design problem or amplifier. It's not a design problem, it's just a calculation based on the amplifiers. And what was given is that this amplifier has an ideal gain of 100. But then again, there are some non-idealities. With the voltage source, you have this RS, which is a non-ideality of the voltage source. With the op-amp or with the amplifier, you have an input impedance. That is another non-ideality. So you'll have a voltage division between these two. Again, on the output side, the amplifier's output has a impedance, which is RO, and RL is the load resistance. So you'll have another voltage division between these two resistances. And what you are asked to find out that what is the overall voltage gain. So what overall voltage gain will be the voltage division at the input side, multiplied with the ideal amplifier's gain, multiplied with the voltage division at the output side. Now, because your RL is 10 kilo, your load is high, and the output resistance of the op-amp is low, almost all the voltage will be available at the output side. So again, if you do the calculation, it would be 10 kilo ohm divided by 10 kilo ohms plus 100 ohms, which is a ratio of almost equal to 1. So you don't even need to consider that output side voltage division. You can just consider this as 1. But the input side voltage division is something you need to consider, because this is 10 kilo ohm and 30 kilo ohm, and both are kind of equal to each other, right? So it's not that you can neglect one of them as compared to the other one. It's good to neglect one of the resistances if one of them is larger by, let's say, a factor of 100x, or at least more than 10x or 20x in your calculation. But if it is 3x, 5x, even 10x, don't neglect the other resistance. So you'll see that this factor is 3/4, and then multiplied with 100, that gives you almost 75 volts per volt, because your output is a voltage, input is a voltage. So that's the amplification factor you're getting, and it's a voltage over voltage amplification. Your output is a voltage, input is a voltage. For the fifth problem, your output is a voltage, input is a voltage, so it will still be a voltage over voltage formula or voltage over voltage equation, but the amplifier's model has changed to something else. In this case, you had a voltage controlled voltage source. Your amplifier model was A times V in, gain times the input voltage. And remember that the input voltage is not this Vs, the input voltage is whatever is available at the input of the amplifier after the voltage division at the input side. So A times that input voltage is your amplifier's output in this case. So this is a voltage controlled voltage source. Your input is a voltage, output is a voltage. for this model, it's a voltage controlled current source. Your input is a voltage. So input is still a voltage which is developed across these two terminals, the input terminals of the amplifier. But the output is a current. And what is this GM? GM is a transconductance. So why transconductance? It's because it transfers an input quantity to the output quantity. And that quantity is conductance. What you transfer from input to output is a conductance. Why? Because your output is a current, input is a voltage. So output divided by input is a conductance. So whenever you're thinking about any transfer function, you'll always think about the output quantity divided by the input quantity. In this case, the output quantity is a current, and your input quantity is a voltage. Right? So this is out divided by in, not to confuse this with current. So out divided by in is a current divided by voltage. You already know from Ohm's law that voltage divided by current is resistance. Current divided by voltage is 1 upon resistance, which is a conductance. So that's why this is called a transconductance, because it's a transfer function quantity that converts an input voltage to an output current. And the value of this GM or the transconductance is also given. Something interesting to note here is the direction of the current. And some of you have already pointed this out and have solved it correctly. Most of you have solved this correctly, that the direction of current is such that there is a current flow from this point to this ground, right? So which means the current flow is like that. Now, if you define your V0 as a positive terminal here and a negative terminal here, and if your current flow is in the opposite direction, you'll effectively have a negative term in your final calculation, right? Because if your voltages and currents align up, you have everything as positive quantities. If they don't align up, you'll have a negative quantity. Okay, so just keep that in mind. But apart from that, I think everyone understood this problem and everyone were able to do the input side voltage division. And what is the output? What is the voltage that you see at the output side? It's basically minus of GM. Why minus of GM? Because again, the current is flowing in the opposite direction. So you do a minus of GM multiplied with effective resistance. What is the effective resistance? The effective resistance is the resistance that you see at the voltage controlled current source looking into the right hand side. Because that's the resistance through which you're driving the current, right? And what's that effective resistance? That effective resistance is 200 kilo ohm, which is the RO, multiplied with or in parallel with this 200 kilo ohm again, which is the RL. Now, because both of these resistances are equal, your effective resistance will be half of any of those, which is 100 kilo ohms. So you have a voltage division at the input side, which in this case, fortunately, is equal to 1. But the overall gain that you see because of the GM and the resistive division on the right hand side is basically this 1 milliampere per volt multiplied with 100 kilo ohms. And that gives you a minus 100 volt over volt. See, again, you have a volt over volt. Why? Because you had a milliampere over volt for the GM. That's the unit of the GM multiplied with a kilo ohm. So milliampere multiplied with kilo ohm, that gave you a volt in the numerator, whereas the denominator you already had a volt. So your units also match up. So this is one way to sort of check whether you are doing the calculation correctly or not. Just look at the units. All right, so you have a minus 100 volt per volt. And what's the meaning of the minus? It just means that your whatever the phase at your input side, again, remember that this is an amplifier, and I have probably told this enough times, but I'll still repeat it, that amplifier amplifies an AC voltage, not a DC voltage. So if you have an AC sine wave at the input side, let's say it looks like this. At the output side, what you will have is a 180-degree phase shifted version. That's all it means by the negative sign. That your input and output are 180-degree phase shifted. That's the meaning of your gain being a negative quantity. And of course, the gain factor is 100. So it will be 100 times bigger, but in the opposite direction, which means whenever you have a positive cycle at the input, you will have a negative cycle at the output. And whenever you have a negative cycle at the input, you will have a positive cycle at the output. So that's the meaning of having a negative gain. That's it, nothing else. So it just means that the phase is 180 degrees shifted or the phase is inverted. All right, any questions? So there are a few more practice problems here, which you can just go through in a solution document. I'll upload the solution document after this class. And there are a few more practice questions which you can do just to be better prepared for the exams and the later homeworks. Any questions here? All right, perfect. So if not, let's go back to the discussions that we were having in the last lecture. And what we said is in the last lecture is that we are now looking into non-ideal op-amps. We already know how to solve ideal op-amps. That was your homework on problem number 4 and problem number 5. Right? So they were sort of, even though there was some non-ideality involved because you had an input impedance and you had an output impedance. But you'll see that whenever you don't have infinite input impedance, whenever you don't have zero output impedance, and whenever you don't have infinite gain, solving an op-amp problem becomes very hard if you apply the nodal analysis, that is KCL and KVL based analysis, or even if you apply the feedback based analysis. So instead, what we started doing in the last lecture was a loop gain based analysis. Now, loop gain based analysis gives you the gain of the non-ideal scenario in a very much simplified form, because what it does is that it represents the non-ideal gain as a function of the ideal gain. So you just find out what is the gain of the ideal op-amp initially. If you had an ideal op-amp in this scenario, let's say this is the feedback network that you have an R2 connected from input side to connected from the output side to the input, and you have this voltage division. And we solve this problem in two different ways in the previous two lectures. We solve it using KCL and KVL. We also solve it using the feedback theories. But in both of those two cases, what we solved was only this A infinity. We assume that this op-amp is ideal. We did not just think about this. If we assume that there is another resistance over here, there is another resistance over here, everything becomes so much more complex. Right? So you can solve it. Of course, you guys are intelligent and you can solve it. But why bother if you have a much easier method? And that's the easier method we are going to learn here. The easier method is that assume that op-amp is ideal and find out what is the ideal op-amp, what is the gain of this system, assuming that there is an ideal op-amp which has infinite gain. You already know this A infinity term, which is the gain of the system, assuming an ideal op-amp, and that is 1 plus R2 over R1. And this is called a non-inverting op-amp configuration because you're applying this input to the non-inverting, you're applying this Vs voltage to the non-inverting input of the op-amp. You're applying it to the positive terminal. There is also another configuration which we learned today, which is called inverting op-amp configuration, where we'll apply the input to the inverting terminal. We'll learn that in a later part of today's class. But this is also called a non-inverting op-amp configuration. And you can also see it from the gain. The gain is a positive quantity, which means that, of course, why am I saying that it is a positive quantity? Because resistances are always positive. Right? You cannot, have you ever seen a negative resistance? Most likely not, right? There are many like advanced concepts in a graduate class where there are concepts of negative resistances, but we'll not go there in this lecture or in this class or in this course whatsoever. So resistances are always positive for all practical purposes. So you have 1 plus a ratio of 2 positive quantities. So overall, it's a positive quantity. So your gain is positive, which means that whatever phase you have at the input side, you'll have the same phase at the output. If you have a sine wave that looks like that at the input, at your output, you will have an amplified version of that, but at the same phase. So this is called a non-inverting configuration. And we already found out the A infinity from the two methods that we learned in the previous lectures. What we are saying now is that the overall gain is that A infinity divided by 1 plus 1 over T, where T is the loop gain. T is the multiplication factor of the op-amp which does not have an infinite gain, multiplied with the feedback resistances or the feedback paths overall gain. And we solved this problem in previous class. right? So how did we solve it? We converted this circuit into the linear model of the op-amp. And the linear model of the op-amp is something that you had learned already, that you have this, this input impedance, you have this A times VD, and you also have this output resistance RO. Now, how we solve this from this point onwards is that we considered this as the entire feedback network. So actually all these resistances. So starting from the output of the op-amp, starting from the output of this ideal voltage source. This is an ideal voltage controlled voltage source, right? Starting at the output of this ideal voltage controlled voltage source, traverse back toward the input side, consider whatever voltage divisions you see, and then put them in a form like this, right? This is what we solved in the last lecture. I'll not repeat it this lecture again, but you already have the recorded video how to solve this. And that gives you your T, that gives you the overall loop gain. And now you just put this formula here, A infinity divided by 1 plus 1 over T, and that would give you the voltage gain when you don't have an ideal op-amp. Similarly, this was another problem that we solved. And in this case, the op-amp is represented as a GM terms multiplied with VD. So you again, any kind of op-amp, depending on whether you're trying to solve a voltage controlled voltage source problem or a voltage controlled current source problem, it can be represented in two different forms. One is this, which is the voltage controlled voltage source or a dependent voltage source. And one is this, which is a dependent current source. So GM multiplied with VD. So you can again solve the entire feedback network in the same manner, and you can find out what is the overall gain. Now, in this case, again, start from this point, which is the output of the ideal current source. And what do you see at the output of the ideal current source? You see a resistance RO, which is the parallel resistance of this current source to represent the non-ideality of the current source. Just like you had a series resistance with a voltage source, you can have a parallel resistance, a non-infinite parallel resistance with the current source, right? And then you look at whatever is connected on the right-hand side. So what is connected on the right-hand side of this RO, so that is your effective resistance looking at this point, is your RO in parallel with R4, because at this point you see RO connected to ground, you'll see R4 connected to ground, and you'll see R2 in series with Rx. So that's your overall effective resistance at this point. And Rx is again something that we had found out before. It will be the same thing, the same formula, and you can write this down as R1 in parallel with Rin plus R3, which was same as before. And you can find out what is the overall loop gain, and the overall loop gain will be this transconductance term. Just like we solved the homework problem number 5, homework 1 problem number 5, it will be the transconductance term multiplied with the effective resistance that it sees on the right-hand side. So transconductance multiplied with the effective resistance will give you a voltage term. And now you look at the voltage division looking into the feedback network. So that's it. It's very similar to what we had seen before, but it's just that this A multiplied with the first voltage division, that's replaced by the GM multiplied with the effective resistance. And the second and third term are the same, because the network is still the same. Right? All right. So this is just an explanation of what I had already told you, and please go through the written document. Next thing we wanted to discuss, and most of you already have gotten some sense of this already, that how to calculate input and output resistances for any network. And this is also part of your lab 1 that you're performing right now. It has, I think today, some of you have started with your lab 1, right? And in your lab 1, you are required to find out some of the input and output resistances. And how do you find out input and output resistances? Let's say you wanted to find out the output resistance of this circuit. And the easiest way to do that is first kill all the independent sources. If it is a voltage source, short it. If it is a current source, open it. because you don't want that voltage or current source to affect your measurements when you are trying to find out the output resistance. And then connect a Vx. So because you are trying to measure the output resistance, connect an arbitrary voltage source Vx at the output side. Now, important thing here is that if you are trying to measure the AC output resistance, which we'll be doing for the rest of the course, and also even in lab 1, you have to connect the AC voltage source. This is not a DC voltage source. You are trying to find out what is the AC output resistance. Okay. So there's a difference. Again, AC and DC are two very different things, and we'll consider them differently in this course and any other future course that you take in analog circuit design or mixed signal circuit design. So this is an AC output resistance. And AC output resistance is the AC voltage divided by the AC current that flows back into the circuit. Okay. Or basically in this case, you had connected a AC current source and measured the voltage that developed. What you can do is that you can put a AC voltage source and measure the current with a multimeter that goes inside the circuit. So both will give you the same output resistance. And output resistance will be this Vx over Ix in both cases. How to find out the input resistance? Again, the input AC resistance. You apply an AC current source. And now remember a little bit in terms of the notation. Whenever you see a small case or a lowercase term like this small I and then x, small x, this usually means that this is an AC current. If it were a DC current, you would normally represent it like Ix. Right? So that's a little bit about notation. Many of you already know this, but I just wanted to make this clear that this means that this is an AC current. This means it's a DC current. Sometimes you'll see a notation like I but small x in books. What that will mean is that you have both an AC current and a DC current. So this is equal to this small Ix plus the large or the capital letter Ix. So you have the lowercase Ix, which is the AC current, and you have the uppercase Ix, which is the DC current. It's a combination of those two, and that is usually represented as an uppercase current with a lowercase node name. So that's what you will find as a usual notation in books. So don't get confused between these three different terms. So a lowercase definition always means that it's an AC quantity. An uppercase definition means it's a DC quantity. And when you have a combination of uppercase and lowercase, it means both are present. And you might have already guessed this, that what is the purpose of this DC quantity is just biasing. So right now I'm showing it in terms of current, but you can also assume that everything is in terms of voltage. So if you had a write the voltage notation, if you had V and then lowercase x, that means that you have an AC voltage at node X, so lowercase v plus an uppercase V at that node X. This means you have a small signal AC voltage as well as a DC voltage. What's the job of this DC voltage? The job of this DC voltage is to establish the biasing. Remember the VTC that we had drawn a few lectures back? So this is your output and the x-axis is your input. You expect gain only in the middle region of your output versus input curves, right? You don't expect gain when your input is very small and output is very large. You also don't expect gain when your input is very large. You only expect gain, AC gain, only when your inputs and outputs are kind of in between the rails. So this is called the voltage rail. And this is usually very close to the VDD or the supply rail. This is usually very close to the ground rail, right? So the value in the y-axis I'm talking about. So this is supply rail, which means it has a high value. This is the ground rail, which means it has a low value. Whenever you are in the middle of the rails, so if you have a 5 volt supply and a 0 volt ground, whenever your DC points are around 2.5 volts, you can expect quite a significant amount of gain from your amplifier. If you have a dual supply, if your VDD is 5 volts and VSS is minus 5 volts, if you have an amplifier, if you have an op-amp which works with 5 volt supply and a minus 5 volt supply, then what is the average of these? What is the midpoint of these? 0, right? So in that case, even around 0 volt, if you apply a AC voltage, you would expect an amplification. But don't expect the same thing if you're applying 0 volt over here. If you apply 0 volt over here and your input is at 0, the DC voltage, DC potential at input is 0, and you have a small signal AC on top of it, don't expect this amplification. Question?
So in that case, you just basically apply a DC offset.
Exactly. So you apply again DC offset, which is an average of these two. Apply maybe 2.5. So apply somewhere over here instead of applying at 0. So have a DC potential of around 2.5 volt. Apply your AC potential, you'll see a large swing at the. Okay, so that's the meaning of bias. That you apply a DC bias so that you can expect gain. So you apply, you heat up your steam engine to 100 degrees centigrade so that water can be converted to steam. If you do not have that temperature at 100 degrees centigrade or 212 degrees Fahrenheit, water will not be converted to steam. Yeah, that's the meaning of biasing. Questions? The supply is always DC. So it's a 5 volt DC. This is a 0 volt DC. Now, I already talked about this in the previous lecture. But what does that mean? That if you have the supply at 5 volt DC, what is the AC potential of the supply? 0. So when you are analyzing AC, when you are analyzing small signal gain, which we'll get to in maybe like 10 more lectures or so, for small signal analysis or for AC analysis, the supply can also be considered as a ground because there is no AC fluctuation in the supply. So this might be a little confusing at first, but I just wanted to mention this so that you remember that whenever we'll do AC analysis, and that will be like 10 lectures away from now, don't worry about this right now. But during those analysis, we'll consider this also as ground, AC ground, or a virtual ground. It's not a real ground, it's not 0 volt. That's why it's not a real ground, it's just an AC ground. What effectively means that there is no AC potential here. Right? Agreed? There is no AC potential in your supply, which means the supply is also an AC ground. It could be confusing at first, but when we solve the actual problems, it will become much clearer. Okay. So we digressed a little bit, but what we were discussing is this AC input and output impedances. And then again, there are multiple ways to do it. You can connect an AC current source or AC voltage source, find out the ratio between voltages and currents that will give you the resistance. That's all it means. And before doing that, you have to kill all the independent sources. That's it. Similarly, you can find your input resistance. And when you are finding your input resistance, let's just assume that this voltage source has a non-ideality, has this RS as a non-ideal series resistance along with the voltage source. Will that affect your measurement of your input resistance? It will not, because your input resistance of the black box is defined at the input of the black box. So whatever is happening before the input will not come into the picture. Your input resistance is defined at this point. So you'll not care about what is there on the left-hand side of it. Makes sense, right? That you are looking into the resistance, looking into this point. The resistance of the circuit does not change if I change this RS from 10 ohms to 100 ohms. The resistance of the input resistance of this black box will still remain same. But because you are looking into the right-hand side, if I change something on the right-hand side, it will change your input resistance. So if I change my load resistance, if I change this RL, it will affect my source resistance, or it will affect my input resistance of the black box. So whatever is present on the right-hand side will affect my resistance when I'm looking on the right-hand side. Similarly, when you are trying to find out the output resistance of the black box. It does not matter if you have connected a load, because the load is on the right hand side and you are looking into the left hand side. If I'm looking into the left hand side, I don't know what is present on the right hand side, right? So when you are looking into the output resistance of this black box, it will not matter how much load you have connected, but it will matter if your source resistance is different, because you are looking into the left hand side and this resistance is on the left hand side. So if you think about it simplistically, it's very intuitive. Whatever you can see will be in your calculation. Whatever you do not see will not be in your calculation. That's it. Okay. So if you want to look into a few examples, and these are not complex examples per se, but these are it'll be very easy if we just look into one or two. Okay. So the first one is this circuit. So you have an op-amp. You have two resistances, R1 resistance and then an R2 resistance in feedback. What we are trying to find out first is what is the input resistance looking into this positive terminal. If you assume that this op-amp is ideal, and let's draw the internal circuitry of the op-amp for that, right? Then it will be even more clear. So I'll connect this here. And for the sake of simplicity, let's just assume that it's a voltage dependent voltage source. So it's this, right? So this is the linear model of the op-amp, that you have V in over here and you have A times V in, and we are assuming perfectly ideal op-amp. So you have an infinite input impedance, so the input side is open. You have zero output impedance, so it is a short. And from the output side, this is your output point, this is this point. You have a R2 resistance. Let's call this plus and minus. So I'll just call this as minus and this as plus. And then you can connect this ground over here, because at the plus terminal, at the positive terminal, the ground was connected. And remember, if I'm defining it like this, then my V in is basically a negative voltage, because I have negative over here and a positive over here. So this voltage will be a negative voltage. But that's for later. So right now, let's just consider that you have this R2 resistance connected from your output to the input side and connected to the negative input terminal. And here you also have an R1 connected to ground. Now, what we are asked to find out is that what is the resistance looking into this port? We know that this port is connected to ground, right? But it is connected to ground on the back side of it. Right now, you are only looking at on the top, right? You are only looking into the upper direction at this point. So you don't care what is present in the other direction. If you're looking into left, you don't care what's there in your right. If you're looking in the upper direction, you don't care what's there on the bottom direction. So even if this is connected to ground, what we are trying to find out is the AC resistance looking into this port. What is the AC resistance looking into this port? Because this is connected to an open circuit, the AC resistance is infinite. Right? You don't care that it is connected to ground. It is connected to ground in this direction. On this direction, it is connected to an open. So whenever you're trying to measure the resistance, whenever you're trying to measure the resistance at that point, what do? You first disconnect the load. So you first disconnect whatever is connected at this point. And then you apply a Vx source, try to measure what is the current Ix. Now, if you apply a Vx source at this point, because this is open, there will be no current flow Ix into it. There will be no current flow into the op-amp. And that's why we are saying that the input resistance is infinite. All right, clear? What is the output resistance? For output, you are looking into this point, right? So we are looking into here, in between these two nodes. And of course, this node is grounded inside the op-amp. So we are looking into this point at your output. What do you see looking into this point? You see that there is a voltage source A times V in, and there is something connected in parallel. Like there is R2 which goes to this V in node, which also goes to R1, and then that goes to ground. Why are we saying that the output resistance is 0? We are saying the output resistance is 0 because the series voltage, the series resistance of a voltage source is 0. Series resistance of an ideal voltage source is 0. So you have a 0 resistance path here to ground. From this point, you have a 0 resistance path to ground because you have a voltage source over here, and the resistance of any voltage source, if it is an ideal voltage source, is 0. So at this point, you see a 0 resistance path here to ground, and you see some other resistance R2 and R1 which also goes to ground. So in parallel, there are two paths. One is a 0 resistance, one is a finite resistance. So what would be the effective parallel combination of those two? It will be 0. So that's why your output resistance is 0 in this case, even if you have these R2 and R1 resistances connected at your output. Okay. What will happen if you are looking into this? So I think we are out of time today, but you look into these rest of these examples, this one, and this one, which are very much self-explanatory. If you just draw this linear model of the op-amp, it will be very easy to understand why this Rin is R1, why this Rin is equal to 0, and why this Rout is equal to infinite. I think the answers are also provided later on, but just go through these problems to have a better idea about input and output resistances. So with that, we will stop here. And in the next lecture, we'll look into a few configurations of op-amp, and then we'll start with our next topic.